In this lecture, we are going to study an important topological structure called the Morse-Smale complex. Similar to how the simplicial complex helps represent a topological space, the Morse-Smale complex helps represent both a topological space and a Morse function that is defined on top of it. It has several applications in data analysis, in the study of scientific data, within various application domains. In this lecture, this first lecture on Morse-Smale complex, I'm going to talk primarily about the definitions and some properties. So I will introduce what are called gradient or integral lines. These integral lines are collected together to form what are called ascending and descending manifolds. The ascending and descending manifolds are represented in the form of a cell complex called the Morse complex, and we will see there are two types of Morse complex that together constitute the Morse-Smale complex. So we will study Morse-Smale complexes for 2D and 3D functions. While the definitions extend to higher dimensions, there are no good algorithms for computing the Morse-Smale complex in higher dimensions, so we will restrict our attention to 2 and 3 dimensions. And to conclude, we will see a practical use of the Morse-Smale complex by connecting it to some of the lectures we have seen earlier. So in particular, we will look at how homology can be computed using the Morse-Smale complex. Let's start with a one-dimensional function. So we have seen the plot of a graph plot of a function earlier. So this is a similar example of a one-dimensional function which has minima and maxima. Now we know how to characterize the minima and maxima. So let's assume that the minima and maxima are already identified. So far we are not talking about algorithms. So this is still working with the analytic description. So we have a smooth function, a Morse function. We have the maxima and minima. Let's go back to the discussion about the stability of points, or if you are on a roller coaster ride, what happens to you if you are at any point on the ride. What I would like to do now is to collect these points based on similar behavior. So to begin with, I would like to identify all those points that will end up at a given minimum if you let go and let the point fall under the effect of gravity. So the green part of the curve indicates all the points that will flow into this one minimum. We call this the ascending manifold. We will talk about these definitions later. Similarly, we can talk about the collection of points that are reached when you flow away from a maximum. So for example, if you are at the maximum that's indicated here, and so this is the maximum, and if you let go of the point and perturb it a little bit, and you try to identify the collection of points that can be reached after this perturbation, then you have this orange collection of points. We call this the descending manifold. You can quickly see that these descending manifolds represent the various mountains in your domain. Right? So each maximum has its own mountain, So similarly for the what we saw earlier for the minimum, each minimum had its own representation of the valley that is represented by that minimum. So so let's look at the descending manifolds here. If I associate such a descending manifold or a curve for every maximum, then I can partition my domain. Now I can take this one step further and overlay the descending and the ascending manifold. So all the mountains and the valleys, right? And now when I overlay, I want to find the various equivalence classes. So earlier the green curves were identified or labeled by the minimum, and the orange parts of the curve were identified or labeled by the maximum. Now we want to label different parts of the curve based on a common origin and a common destination. So the brown curve here, for example, is the collection of points that flow from this maximum and flows into this minimum. So again, you can imagine that the entire one-dimensional domain can be partitioned into such brown curves, each of which is defined by a pair, an origin-destination pair. So this partition will be called the Morse-Smale complex, and each entity within this complex will be called a Morse-Smale cell. So this is the intuition for the topic of today. Let's see how this notion extends to 2D, and while doing that we will try to formalize the notion and give proper definitions. So now we are talking about a 2D function. So what I have shown here, the running example, it looks like a terrain. So each curve here, if you try to trace each closed curve, this is the collection of points at a given height. So this is an isocontour. So you can imagine how this this terrain would look like, right? This is a very often used representation of a 2D function. Let's use this running example and try to introduce the notion of the Morse-Smale complex formally. So to begin, I need the notion of an integral or a gradient line. So here is a picture. An integral line is just this curve where at any point on the curve, the tangent to the curve is equal to the gradient of the function at that point, right? So at every point, if you look at the tangent, that is exactly equal to the gradient. So the integral curve, or the integral line, or the gradient line as it is also called, is defined as a maximal open curve whose tangent at any point is equal to the gradient of the function at that point. So note the two terms, the curve is maximal and it's open, so there is no boundary. So this is like an, so what happens at the boundary? So you can imagine that you trace this curve by following the gradient, and as long as the gradient is non-negative, you can march along this integral line. As you get closer and closer to a critical point where the gradient becomes zero, right? You take smaller and smaller steps So you never essentially reach the critical point. So hence the curve is open. The boundary of this curve is essentially the critical point. There are two boundary points, as you can see. One is called the origin and the other is the destination. These are natural names. So in this particular example, the boundary would be an origin here and a destination somewhere here. So what are the properties of this integral line? The boundary points of the integral line are critical. So that's exactly where the gradient goes to 0. Two integral lines can never intersect, because if they do intersect, then the intersection at the intersection point, you know that the gradient is uniquely defined. If the two integral lines intersect, then then this is no longer true, right? So two integral lines can never intersect. And another interesting property is that the integral lines, the collection of all integral lines, will cover all the regular points in the domain. This is also easy to see. So we want to now use these properties to define different partitions of our domain. So let's start with maxima. So note that the integral lines go along the direction of gradient. So if you are in a terrain, then the gradient is pointing up, increasing direction of the function, right? So the function is height. So if you're pointing upward in terms of the gradient, then you are marching up the hill. So you pick any point as shown here by this orange point, and you begin tracing the integral line that passes through this point. You will walk along this orange curve and move towards a maximum. You collect all the points that march towards this common maximum, and you have the descending manifold of that maximum. The reason why this is called the descending manifold is that when so this entire manifold is defined by the maximum, and you are essentially descending from the maximum to trace the entire manifold, hence descending manifold. So let's look at the structure of this descending manifold. This is how it looks like. All the integral lines that reach this particular maximum. Now clearly this descending manifold has a boundary. So part of this boundary is here. Right? And then there is the other part which is here. Right? And then there is the natural boundary of the domain. So similarly, one can talk about the descending manifold of a saddle. So for a saddle point, you want to think about all the integral lines that end up at this saddle. It turns out that this is essentially a one-dimensional arc. So this is how the integral line for a saddle looks like, and this particular what you see on the right comes from here. On the in the figure, it comes from here. Right? So if I look at what bounds these descending manifolds, then you see that the descending 2 manifold, so note that since the integral lines cover all the points, you do have a manifold, and it is 2-dimensional for the maximum, right? So hence descending 2 manifold. So what bounds this descending manifold? It is essentially all those arcs between maxima, between saddles and minima. So these are descending 1 manifolds of the saddles. So the descending 2 manifold is actually bounded by a collection of descending 1 manifolds. Similarly, the descending 1 manifold of a saddle is bounded by descending 0-dimensional manifolds, which are essentially just the critical points, minima. The 2 minima that I'll try and draw here. So these constitute the boundary of the descending 1 manifold. Right? So you already see that there is this nice structure that we have seen from simplicial complexes, except that we don't have simplices anymore. We have these descending manifolds, and their boundaries are also descending manifolds, and so on. Before we formalize these collections of descending manifolds as complexes, let's look at the ascending manifolds as well. So given a minimum, let's look at all the points that can be reached from this minimum via a integral line, right? So the blue integral line takes you from the minimum towards different points in the domain, and you attribute all those points, all those green points, to that minimum. So all those points have a common label, the green label, and all that corresponds to a single minimum. So this is called the ascending manifold of the minimum, and you can again see that this ascending manifold is 2-dimensional, hence an ascending 2 manifold. This is how the ascending 2 manifold looks like. The saddle also has an ascending manifold. The same saddle that we saw earlier has a ascending manifold as well, and it looks like this, what you see on the right. Again, we can talk about what bounds these ascending manifolds. The ascending 2 manifold is bounded by a collection of ascending 1 manifolds. So these lie between saddles and maxima. So you can imagine that the ascending 2 manifold of a minimum is the valley that is defined by this minimum, and the boundary of that valley consists of the various ridges and the mountain tops. That's the collection of ascending 1 manifolds. Similarly, the boundary of an ascending 1 manifold is a collection of the 2 ascending 0 manifolds, which are the maxima. Right. So the ascending manifolds essentially behave very similar to the descending manifolds. We will look at this actual notion of duality soon. So what are the dimensions of the different ascending and descending manifolds? We saw that the descending manifold of a maximum is 2-dimensional for a 2D function, right? So this is true in general. The descending manifold of a critical point with Morse index I is an I-dimensional manifold. So this is a manifold because it is open, there is no boundary, so all the points have a local neighborhood that looks like Ri, right? So that's why I call this descending manifold an open cell of dimension I. So in the terrain case, the descending manifold of a maximum which has index 2, right, is two-dimensional. The ascending manifold of a critical point with index I, on the other hand, is an open cell whose dimension is the dimension of the manifold minus I. So again, the same example, the ascending manifold of a maximum, the maximum has index 2, the ascending manifold of that maximum, it has dimension 0, because you cannot ascend from the maximum anywhere else except stay at the same point. Right. So you already would have noticed the duality between the ascending and descending manifolds. Formally, the ascending manifolds of F are the descending manifolds of minus F. Now let's talk about how we can represent these ascending descending manifolds. The ascending manifolds form a so-called cell complex. Analogous to the simplicial complex, a cell complex is a collection of cells that satisfy the same properties that we saw for a simplicial complex, namely the subset property and the property about common faces also being cells of the cell complex. The boundary of an ascending manifold, we already saw, consists of lower dimensional manifolds. We know that two manifolds do not intersect because two integral lines do not intersect. And since the integral lines also cover all the regular points, the critical points are all the boundary points. So we know that the ascending manifolds together partition the entire manifold M. Similarly, the descending manifolds also form a cell complex. This is a dual cell complex, and they also partition M, right? So this is how the cell complex looks like. So this is another pictorial depiction where the maxima are shown in blue, the minima on the right are shown in gray, and the saddles are shown with this plus symbol that indicates the direction in which the function increases and the direction in which the function decreases within the local neighborhood of the saddle. So the ascending manifolds are illustrated on the right for every minimum using these pink regions for the minima, the light pink, and on the left the descending manifolds for the maxima are indicated by the dark pink. So the entire descending manifold is not shown just to avoid clutter. So this cell complex, for example, the descending manifold is represented as a cell complex. The two-dimensional cells are the dark pink regions. The one-dimensional cells are the arcs between the saddles and the minima, and the zero-dimensional cells are the critical points themselves. Similarly, the ascending manifolds is also represented by a collection of cells. So these cell complexes are called the Morse complex. So you often talk about Morse complex of maxima and Morse complex of minima. The Morse-Smale complex is defined as the overlay of the two. So again, using the same illustration as before, if you overlay the two Morse complexes, you get the Morse-Smale complex, where every maximum has an associated descending manifold, which is shown in dark pink here, which is further partitioned by the overlay with the ascending manifolds. So in order for this to be well defined, we need this notion of origin and destination again. So the each cell in this Morse-Smale complex is a collection of integral lines that begin and end at a given pair of critical points. So for example, the cell that is shown here with the arrows, with the integral lines, is the collection of all integral lines that that share a common origin minimum and a common destination maximum. So this is a two-dimensional cell. This is one of the cells of the Morse-Smale complex. So in order for the Morse-Smale complex to be well defined, we need the notion of an additional notion where the integral lines have only transversal intersections. As in, if you have two integral lines, then we know that they don't intersect, and we know that they can share a common origin and a destination, right? But it is quite possible for two ascending or an ascending and a descending manifold to intersect. Now we want those intersections to be transversal in the sense that they intersect only once. So for example, you pick any ascending one manifold, right? You pick any ascending one manifold, so such as one of these dotted lines, right? So this is an ascending one manifold. So this is a descending one manifold. Well, depending on the, I take that back. So this is an ascending one manifold. Since we are talking about one manifold, this is an ascending one manifold of the saddle. Here is another ascending one manifold of the saddle, right? How does this intersect with the descending manifold at the saddle? The two intersect exactly at the saddle, right? And they share a common boundary point. That's it. So this is called a transversal intersection. So we would like intersections that are of this nature, right? We do not want intersections such as this, right, where the two curves touch each other for some time. So this is not a transversal intersection. So this notion extends to higher dimensions also. So for example, if you have a surface, right, and you have so this is a descending two manifold, let's say, right, and you have an ascending manifold. You want the ascending manifold to intersect transversally exactly at one point. You don't want the alternate is that you have a non-transversal intersection would look like this. right? So we don't want such intersections between ascending and descending manifolds. A transversal intersection ensures that the overlay results in a collection of cells. So this is the reason we want transversal intersection. Just like how we saw for Morse functions, you can perturb any smooth function to ensure this Morse-Smale property. So in practice, we don't worry about this so much. But assuming that the ascending and descending manifolds always intersect each other transversely, the cells of the Morse-Smale complex are nodes, as you can see here, the critical points. There are arcs that are the arcs from the saddles, and then you have the two-dimensional cells which happen to be quads. So you will notice that all the two-dimensional cells here are quads. We will actually see why this is so, right? So before talking about the combinatorial properties, let's look at the Morse-Smale complex again. So here is another terrain with a few maxima, just two maxima, and a collection of valleys or minima surrounding the two maxima. We can see that the Morse-Smale complex partitions the entire domain, and we know how these individual cells are defined, right? So each cell is a collection of integral lines that have a common origin and a common destination. Now we know that the interior of this cell does not have any critical points, right? So in that sense, these cells are monotonic. So what the Morse-Smale complex gives you is a decomposition of the domain into these monotonic cells, right? Monotonic as in no critical points in the interior. So strictly increasing, strictly decreasing, right? Either one. So this is the partition. But we can often think of the Morse-Smale complex as just a graph. So this is called the combinatorial structure of the Morse-Smale complex, what you see on the right, where essentially you capture just the combinatorics and throw away the geometric representation of the arcs and the cells. This turns out to be quite useful in practice. Of course, what you have on the left is the decomposition into monotonic regions, and this decomposition is not captured when you talk about the combinatorial structure. So in the next few slides, we'll talk about the combinatorial structure, and several applications end up using this combinatorial structure and optionally use the decomposition. So you can also think about this combinatorial structure as one which abstracts away all the numerical components. So what do we mean by the combinatorial structure for a 2D Morse-Smale complex? The nodes of the Morse-Smale complex are exactly the critical points. We have seen this already. All the origins and destinations are critical points, and these are the zero-dimensional cells or the nodes. The saddles have exactly 4 arcs incident on them, coming from the ascending manifold and the descending manifold. A typical two-dimensional cell looks like this, like we saw in the examples. It turns out that all the regions, all the two-dimensional cells are actually quads. Why is this true? So here is an argument. We know that the boundary of any two-dimensional cell alternates between a extremum and a saddle. This follows from simple combinatorics. You start from a minimum and you follow one of the arcs. This arc will connect you only to a saddle, and you know that in the local neighborhood of the saddle, the function alternates between going up and going down. So you know that once you go up towards the saddle, you have to continue going up towards a maximum, right? And then from a maximum, all the arcs that are incident on the maximum are towards saddles again. So you pick the first one in counterclockwise direction in this case, that goes towards the saddle again, right? And the same argument for the saddle, you will have to reach the minimum, right? So we know that the boundary of any two-dimensional cell alternates between saddles and extrema, right? But this is a very special case. What you see here in the lower picture is a very special case where this alternates happens only once, right? So in general, this can happen multiple times. So let's say a two-dimensional cell of the Morse-Smale complex has 4k nodes, because it alternates between minima, saddle, maxima and saddle. So that's 4, and let's say this alternates k times. So there are 4k nodes in the boundary of a two-dimensional cell, right? What happens, here's a thought exercise. Let's duplicate this Morse-Smale complex that you get, right? So let's duplicate this and glue it to itself. So this is a thought exercise that you will have to take up, right? So the Morse-Smale complex that we have has many cells. Each cell has each two-dimensional cell has 4k nodes, right? So you pick one of them, the one which has 4k nodes, you duplicate it, right? So you duplicate it and then glue that duplicate copy to itself, right? So so you have for example maximum and then saddle followed by minimum, it should be a minimum followed by another saddle, followed by a maximum, followed by another saddle, and then a minimum, and so on, right? So you take take a copy of that same cell, right, and glue it. You glue the corresponding points, right, on the boundary, along the boundary, not the interior, just along the boundary, right? So what happens to the maximum when you glue this one disk from the left with the disk that you get from the right? So you have these two disks and you are gluing them only along the boundary, right? So this maximum is glued with the corresponding maximum copy here. So the glued point also remains a maximum because its neighborhood is again smaller, so that remains a maximum. The minima remain minima. The regular points on the boundary remain regular points, so these are all the regular points, they remain regular. But what happens to the saddles? You can convince yourself that the saddle becomes regular. All the saddles become regular points after gluing, right? So just look at the neighborhood structure of the saddle that we saw in the previous lectures, and you can convince yourself that the neighborhood becomes regular after gluing, right? So the glued cell now has 2k minima and maxima. It has 2k minima and maxima, right? And we know that the Euler characteristic can be computed as the alternating sum, right? What is the alternating sum? So the alternating sum, because there are 2k minima and 2k maxima, so the alternating sum is also 2k, right? And what is the glued structure we have? The glued structure is two disks glued on the boundary, right? So when you take two disks and glue them on the boundary, you get a two-dimensional sphere, right? What is the Euler characteristic of the two-dimensional sphere? It is equal to 1, right? So we know that the Euler characteristic is 1, we know it is equal to 2k, so k equal to 1. So hence all the two-dimensional cells are quads. Let's look at some pictures of a descending manifold for an object that is scanned. Let's say a hand which is scanned via something like a Kinect sensor, right? So the domain here is the surface of this hand. And the Morse function defined here is not so important, but what you see are the maxima of this Morse function. So there are multiple maxima of the Morse function. You can see that the maxima are located at all the tips of the fingers and the base of the hand, and there is a couple of maxima at in the palm. There is one maximum here at the palm and one here. All other maxima are at the tips, and you have the descending manifolds of all these maxima, right? So this descending manifolds give you a good partition of the hand into these regions. So if you choose the function appropriately, you can actually get a nice segmentation into parts. And in fact, this is possible even with this function after you apply some noise removal and simplification. So a further simplification will give you a nice segmentation into the four fingers. Somehow the thumb does not get segmented out from the palm. So this is not a foolproof technique for segmentation, but you can see that it seems to work. Another example is to apply this segmentation to get the teeth segmented away from the jaw, right? So again, you see on the top different segments, each one capturing, for example, the different teeth, and one capturing the base of the mouth and so on. The segmentation is not great, as you can see from the other view. So the technique as applied naively may not give you the result, but what you can actually see is that there are small segments. There are small segments that are here, right? All that can be simplified away. To to generate coarse segments. So this simplification is something that we will get to in a future class. So now that we have seen the definitions of the Morse-Smale complex in 2D, I will want to talk about the same definitions in 3D, but I will go through it quickly because the definitions are the same. You can look at the pictures and understand this better. The descending manifolds are similarly defined in 3D. The descending manifold of a maximum is 3-dimensional. The descending manifold of a minimum is 0-dimensional in the lower right. And for the saddles, again it is, for the 2 saddle, the descending manifold is 2-dimensional, and for the 1 saddle, the descending manifold is 1-dimensional. The ascending manifolds have a dual structure, as we have seen before. The cells of the ascending descending manifolds can be collected together to form the Morse complex. So here is the Morse complex of the descending manifolds for a very simple function. So maybe I'll just say what the function is. The function has a single maximum at the center, and you can see that the different vertices of this lattice grid are occupied by critical points. So the maximum is at the center of this cube, and all the vertices on the boundary are either minima or saddles. So the minima are at the 8 vertices, 8 corners of the cube, and the edge centers have the 1 saddles. The face centers have the 2 saddles. So naturally the entire cube is the descending manifold of the maximum. You can similarly compute ascending manifolds for each minimum. That's shown in green here. The intersection computed, the intersection between the two or the overlay will give you the Morse-Smale complex. So here is a cell, individual cell in brown of the Morse-Smale complex. This is a 3-dimensional cell, and in general this 3-dimensional cell looks like a crystal with 1 minimum at the bottom, 1 maximum at the top. So just bottom and top is just for illustration. The orientation can be in any way. And the boundary of this crystal has all the 2 and 1 manifolds. 2 and 1 saddles. All the boundary 2-dimensional cells are again quads, similar to the 2D case. So if you look at the boundary of this crystal, it looks like a 2-dimensional Morse-Smale complex. If I have to again talk about the combinatorial structure, the nodes are the critical points of the Morse-Smale complex in 3D. The arcs connect critical points whose indices differ by 1. So you have arcs between 2 saddles and 1 saddles, minima and 1 saddles, maxima and 2 saddles. All the 2-dimensional cells are again quads. The crystals can have different sizes, but they always have 1 minimum, 1 max, and all the quads on their, all the two-dimensional cells on their boundary are quads. As before, the arcs connecting the saddles, they will have a ring of 4 quads around them. So you can imagine this by looking at the example of a so here is a 2 saddle, and I'm showing the descending manifold as a plane here, a kind of vertical plane, right? And So you can imagine that there is, so this is a two saddle. So the descending manifold looks like a two-dimensional domain. It's two-dimensional, and the ascending manifold will be one-dimensional, right? Now you can imagine that there is a different color. There is a one saddle sitting here, right, whose ascending manifold is two-dimensional, right, whose ascending manifold is two-dimensional, and it intersects transversally with this descending manifold, and this is the transversal intersection. So these two planes, they are orthogonal to each other. Well, they need not be orthogonal, it's just that the intersection is transversal along the brown arc that I have drawn, right? So what this last point is saying is that the arcs that connect the saddles, so here is an arc, the brown arc that connects the two saddle with the one saddle, right? So this arc has a ring of different quads around it, right? So what are the quads? There are two quads that come from the green descending manifold, and two more quads that come from the cyan ascending manifold, right? So we are talking about the ring of quads around this arc, right? So this is an important combinatorial structure. Again, requires some imagination to understand why this is true. Let's conclude this discussion by talking about one quick application. So we are talking about homology computation. So the typical input is a simplicial complex, which is a triangulation of some topological space X, right? And we know how to compute the homology of this space using the simplicial complex K, using the boundary matrices and so on. Here is an alternate solution. I design a Morse function f on K. Let's assume I know how to do this, right? I design a Morse function on K. So this is, of course, a piecewise linear function which satisfies all the properties that we need for the Morse function. And I compute, let's say I know I have a good algorithm for computing the Morse-Smale complex. Let's say I use that algorithm to compute the Morse-Smale complex of f. We know that the Morse-Smale complex is a cell complex, and the union of the interior of all these cells in the complex, they cover this entire space, and hence the cell complex behaves similar to the simplicial complex. It is, we don't call it we could call it also as a triangulation, although it's not a decomposition into triangles, but it is also a representation of the topological space X. In the next step of the algorithm, we store the boundary maps but now of the cells of the Morse-Smale complex, right? So the two-dimensional cells have boundaries which are arcs. The one-dimensional arcs have boundaries which are nodes, and so on. So this boundary map can be stored in the form of a boundary matrix, right? Then we can apply our standard matrix reduction algorithm that you saw, reducing the matrix to the Smith normal form to compute the homology. And since the cell complex also represents the topological space X, this will also give you the homology of the topological space X. So here, let's pause here and think about the running time. So what was the running time of the matrix reduction algorithm? Maybe you can pause and think about it. No matter what, so maybe you've thought about it, maybe you've found the answer. So no matter what the running time is of the matrix reduction algorithm for simplicial complexes, the algorithm that we have seen here will be faster, simply because we are applying the same algorithm but on a much reduced complex. So the sizes of the matrices are much smaller, right? Of course, this is not guaranteed, but in practice, the number of critical points and the number of on the size of the Morse-Smale complex is much smaller than K. Several orders of magnitude smaller, and hence you will end up with a faster algorithm for computing homology. So several software tools that are available. One example is GUDHI, GUDHI. So this we will talk about this later, but let me write this down. This is called GUDHI. So among various techniques, they employ this technique of computing the Morse function and the Morse-Smale complex to efficiently compute homology. So with that application, I will end this discussion on the introduction to Morse-Smale complex. In the next lecture, we will talk about an algorithm for computing the Morse-Smale complex.